welcome back. So if you recall, in the last lecture we had been discussing about LEDs. A lot of things have been discussed in terms of efficiency, extraction loss, escape cone, total internal reflection loss and other things, right. So all these things are building up our understanding of LED. Also the electrical properties, the series and the shunt resistance that can affect your LEDs adversely, and how different LEDs of different colors which correspond to different band gaps have their different turn on voltages, non-radiative recombination, radiative recombination efficiencies, all these things we have covered. So we are pretty much done with LED, except that today I told you that today's lecture will be a brief discussion on the visible LED, the aspect of visible LED, because all the LEDs that we have been talking about are of any color including UV and IR that are not sensitive to human eye. But if we talk about visible LEDs or white light LEDs or bright LEDs that we use for illumination and other purposes which are sensitive to human eye, then we have a a more subjective kind of a discussion on the LED with respect to human vision. It is not a part of any course, exam or syllabus, but you should be aware of in general, because this is a very useful information when you try to understand optoelectronic devices and LEDs with respect to human eye. Okay, so we'll come to whiteboard here. So today we'll conclude LED and we'll discuss some of the fundamentals that are related to human eye and LED, for example. Okay, so these are called photometric qualities. Okay, these are called photometric qualities. I'll come to what photometric qualities are. And then eye sensitivity, there is something called eye sensitivity. Okay, your eye is not sensitive to all wavelengths equally, even within the visible. Okay, and there is something called colorimetry. Colorimetry is the science of color. There are some very interesting and intriguing questions that will come up along this. Okay, so we'll come to that. So human eye has many regimes. Okay, human eye has many. The vision of human eye can be broadly defined into three categories. One is called scotopic vision. This scotopic vision is the vision that gets activated during the night time, or especially like very dark, like no moon, for example, no moon, very deep night sort of thing. Dark, very dark environment you have, for example, then human eye vision is called scotopic vision, that adjusts to the darkness. It is mostly a vision which is mediated by rod. Human eye cells are basically made of two kinds of cells, one is rods and one is cones. These rod cells are more abundant and they are sensitive to visible. Cone cells are pretty much sensitive to only RGB, red, green and blue. Okay. In the scotopic vision, in this dark and a very dark environment, like there is no moonlight, outside it's dark, no electricity, that kind of vision is dominated by rod, and your sense of color is lost in the scotopic vision, because in the night time you cannot distinguish between color in the darkness, right. So that is that vision where you lose the color. These are important parts of LED, actually visible LED, that's what I am talking about. Then in case of, say, then there is something called mesoscopic vision. Mesoscopic vision, and mesoscopic vision kicks in your eye in terms of something like, say, full moon light. It's not very dark, but it's not super bright also, like full moon night, or early twilight, like early dawn, like before sunrise. So this kind of, when it is like between bright and darkness, then you have mesoscopic vision, which has both rod and cone contribution vision. And the third category is called photopic vision of human eye, which kicks in, that vision kicks in when you have like brightly lit office, bright indoors, office indoors, or proper sunlight, outdoor sunlight. And here you primarily have a cone mediated vision. So you have a strong sense of color, and that color is mediated primarily by RGB. Okay, the human eye senses that. Okay, so that's about the human vision. Now those vision, that the reason I talked about vision is because the photometric units of LED or any light source are related to the vision of human. So what are photometric units? These photometric units are units of the quantity, like photons, energy, power, all these things, as perceived by the human eye. Those are called photometric. So when you talk about units in general, something like, say, photons or photon energy or photon wavelength and all these things, these are for generic electromagnetic waves that may or may not be sensitive to human eye, and we call them radiometric parameters. Okay, the moment we talk about photometric parameters, we only talk about those parameters which are as perceived by the human eye. Okay, as perceived by the human eye. So the first important photometric unit is called luminous intensity. You might have heard this word. Okay, luminous intensity. What is luminous intensity of a source? Suppose I have an LED or I have an incandescent lamp, I have a tube light, I have a CFL bulb. Their luminous intensities might be different. Luminous intensity actually is the light intensity. Okay, luminous intensity is the light intensity as perceived by the human eye. As perceived by the human eye. Okay, that's called luminous intensity. And the SI unit of luminous intensity is called candela. Okay, CD. Candela is the SI unit of the luminous intensity, and 1 candela, this comes from candle by the way in the olden times. This is the light intensity as perceived by human eye, and luminous intensity unit is candela. 1 candela is actually the luminous intensity of a monochromatic light, okay, single wavelength light, which is emitting an optical power of 1 by 683 of a watt at 555 nanometer, which is pure green. Okay, that is because human eye is the most sensitive at this wavelength, you will see that. Okay, human eye is most sensitive to green. Okay, 555 nanometer. So at 555 nanometer, if there is a single wavelength light, monochromatic light, that is emitting a power, total optical power of 1 by 683 watt over a solid angle of 1 steradian. In what direction? In all direction. In the solid angle, 1 steradian angle, solid angle, because it's 3D, no, then that amount of luminous intensity is called candela. Okay, that is called candela. Okay, and a related important quantity is luminous flux. These are terms that are used to quantify and compare light sources like tube light, CFL bulb, even your earthen lamp, the diya that you light in Diwali for example, and LED bulb, everything you can compare with these quantities: luminous intensity, luminous flux. Luminous flux is actually the light power perceived by the human eye. Light power as perceived by the human eye. Okay, light power as perceived by the human eye, and the SI unit of luminous flux is something that you know more, use frequently. It's called lumen. LM, lumen. Okay, lumen. Candela is luminous intensity, lumen is luminous flux, and I told you luminous flux essentially is the light power perceived by the human eye. The definition is very similar to that of luminous intensity, except that here we will say that 1 lumen of luminous flux is actually corresponds to a monochromatic light that emits a power of 1 by 683 watt at 555 nanometer in all direction. There is no concept of it should emit only in 1 steradian. 1 steradian is basically 1 solid angle in a way. Okay, in a particular, like when you talk about 2D, you can say that this is the light emitted at an angle of 90 degrees, so and so and so, within a cone of 90 degrees and so. But 1 steradian is in 3D. That condition comes in candela in intensity, but in power is the total power. So no condition of steradian. So essentially 1 lumen corresponds to the power of a source that is emitting 1 by 683 watt at 555 nanometer. That's it. Okay, and that's why you can say that a candela, the unit candela is actually lumen by steradian. Okay, lumen by steradian, and of course 4 pi steradian is the total solid angle. So in a case of an isotropic source, which means it's emitting in all direction, okay, if it's emitting in all direction in 3D, then 1 candela is actually 12.57 lumen. Okay, that's the conversion rate, corresponds to 12.57 lumen. It's not equal to, is the corresponds thing. Okay, when you normalize it, the steradian. Okay, these are the parameters that you compare LEDs, for example. That's why I'm talking about this quantity. Okay, so and the third parameter is illuminance. Illuminance. Okay, ILLUMINANCE. Illuminance, and the unit is actually called lux, or you can say LX. Illuminance actually is luminous flux per unit area divided by area. Okay, so this is lumen per meter square or centimeter square. You are normalizing with the area. So for example, on a clear night, this luminous flux or illuminance or lux gives you an idea also of the power and the brightness only. So for example, on a clear night with no moon, if there is no moon on a clear night, no cloud, no moon, no electricity nearby, then the illuminance is around 0.002 lux, very low. Okay, the surrounding ambient brightness. On a clear night, which is full moon, okay, which is full moon, you have around 0.2 to 1 lux, right. Inside a living room, when you have a light glowing and inside a family living room, you will have 50 lux, okay, illuminance. Sunrise or sunset, when you are getting sunset or sunrise, it will be between 300 to 500 lux, that is the illuminance of the environment. Okay. On an overcast day, which means there is a cloudy day in the afternoon, it is 1000 lux. Okay. In a typical daylight, say morning 10 o'clock or afternoon 3 o'clock and so on, okay, that would be around 10,000 to 15,000 lux. Okay. And direct sunlight at noon, if you have direct noon sunlight overhead, that is around 32,000 to 130,000 lux. Okay. 1.3 lakhs. So, this is just an idea of the illuminance, the around the surrounding thing. So, when you discuss about LED, we have to compare with respect to this, like how much is the LED giving. You will see that CFL bulb or tube lights and other things, those cannot match the illuminance of a LED, especially with respect to power. At very low power it can give you much higher brightness, that is the beauty of LED. I am talking about visible LED as perceived by human eye. Okay. So, that is why there is something called eye sensitivity function. The eye sensitivity function, like how is the eye sensitive, what wavelength is the eye sensitive. So, eye sensitivity function is called something like V lambda, because it is a function of lambda, and lambda, suppose I go from 300 nanometer to suppose 800 nanometer. So, this is eye sensitivity function, this is an arbitrary unit. If I can normalize it actually. So, this is 1, matlab is the eye is more sensitive there, and it goes as logarithmic 0.1, 0.01, 0.001, and this is suppose 10 to the power minus 4. So, it is a logarithmic scale. On the y axis is this thing scale. So, the eye sensitivity function will go something like, okay, x again, let me draw it again. Eye sensitivity function will go something like sorry, it will go, it will not go very slightly, it will go steeply here, it will go like that, then it will fall back like that. Okay. It will fall back around 750 nanometer, and here it will be around 370, maybe 380 nanometer. Okay. And your peak comes at around 550 nanometer, 555 nanometer. Okay. So, this is green, this part is green. Okay. This is green when it is more sensitive. Just to the right of green you have, you cannot see it probably, this is yellow. Okay. You cannot see it probably, and then you have orange, right. Then you have red, red is large, this is red. Okay. And then you have of course cyan, like here, then you have blue of course, then of course you have violet. Okay. That is how your eye sensitivity function looks like. It is a very quantitative kind of thing, and this is how human eye responds. Okay. So, this is the peak is around 550 nanometer, is green, and this eye sensitivity function can be approximated by 3 polynomial. A 3 polynomial can be used to approximate that. That is why it is called a trichromatic, matlab because RGB, red, green, blue, right. It is a trichromatic functions, color matching functions can be used to mimic the human eye vision. You can use 3 functions, x of lambda, y of lambda, and z of lambda, and their addition has to be 1. The total summation has to be 1. It is the eye sensitivity function. So, z of lambda is also 1 minus x of lambda minus y of lambda. Okay. So, these are 3 polynomial functions which are used to mimic this particular eye sensitivity function can be mimicked by that. Okay. It can be mimicked by that. The science of color, is called colorimetry. Science of color is called colorimetry. Okay. The science of color is called colorimetry. It is a bit subjective. There are many organizations that will have their own principles, but typically we follow International Commission for Illumination. And so, using these 3 polynomial functions, x of lambda, y of lambda, and 1 minus x minus y, we should be able, people try to match the human eye sensitivity function. So there is, to get any color or any perception of any color, you can use different fractions of this x and y and z lambda, and so that diagram that will portray any color is a function of x and y and lambda. This is called chromaticity diagram. Okay, chromaticity diagram. Okay, chromaticity diagram, we will show that. Okay, chromaticity diagram. So how do this x and y and z look like actually? So essentially I will show you here. So essentially you have this color matching functions, this x, y and z are called color matching functions. So if you plot the color matching functions x, y and z, and this is lambda of course, so you will see that x, for example x will have a function like this. This is your x of lambda, this you will keep it around 600 nanometer, and this you will keep it around say 450 nanometer. Then you have y will probably be around something like this, and the peak of y will be around 550 nanometer. Okay, red, green and blue of course. And then you have z, this is sorry, this is y of lambda. Okay, and then you have finally z of lambda, which is basically 1 minus x minus y. Z of lambda will be something like that. Okay, and this peak will be around say 450 nanometer maybe. Okay, it's the peak is almost the same as this point. So these are three functions, these are z lambda, and the summation of this, all these three has to be 1 in terms of the normalized value. So these three functions, RGB function, in a way you can call x lambda, y lambda and z lambda. Okay, these three functions are called color matching functions. Okay, color matching functions, and by taking any value on this, by doing a mix and match of these three functions, you should be able to replicate the human eye sensitivity diagram, which is V of lambda. The human eye sensitivity diagram can be replicated by this. Okay, so how much fraction of this is needed? For example, the addition of x lambda, y lambda and z lambda has to be equal to 1. So maybe I can mix up, say for example, if I mix up 0.1 of x and then I mix up for example 0.2 of y, which means z will be equal to 0.7, then what color will you get? If you mix these up, what color will you get? So that is called chromaticity diagram. You can Google up what is chromaticity diagram. You will see that chromaticity diagram, on the, this will be y coordinate, so it will be y lambda. What is the value of y lambda you are taking? This will be x lambda, and z lambda will be 1 minus x minus y, so that is not portrayed here. The chromaticity diagram will look something like this. Okay, I will draw it. It will look something like this. Okay, it will look something like this. This part loosely is like blue violet, and it gradually becomes slightly bluish, this part, this side. This part is green. Of course the intensity varies, dark green, light green and all these things. This part is green. This part is sort of whitish and faint, like almost colorless. Okay, this part is orange and like yellow and amber color, like orange color sort of thing. This color is like red. Of course this part is like, you can say it's like purple, red that goes towards red and so on. Okay, so this part is around green, this part is around blue, this part is around red, this part is around orange and yellow, right, and this part is around white, that part is around white in between. So these values are starts from 0 here, so this will be 0.1, this might be 0.2, 0.3, 0.4 and so on, and this might be also like 0.1, 0.2, 0.3. These are values of x and y that you are taking. So for example, if you take a value of 0.4 in maybe 0.3 in x, and then maybe 0.3 or 0.2 in maybe y, and you come here and you get 0, you get a whitish color, which means if you have almost equal quantity of x and y and z, which means if red and green and blue are almost equal quantity, 0.3, 0.3, 0.3, then you will probably get around white color. If your x component is more, then you will get more red. If your y component is more, you will get green. Of course if your z component is more, which means x and y both components are low, x is 0.1, y is also 0.1, that means z is higher, then you will get blue, because z is more corresponding to blue. So this is called chromaticity diagram, and any LED or other things have to be compared with respect to the chromaticity diagram. Okay, so that is the thing. Okay, there are many things associated with this chromaticity diagram. Let's not go into so much there, but so when you have LEDs, so I'll talk in respect to LEDs now, because LED is what we are interested in, right? So this chromaticity diagram, on this chromaticity diagram, this is Y lambda, this is X lambda, of course. On this chromaticity diagram, I'll use the black color only. On this chromaticity diagram, which looks like this, right? Now please recall to the previous figure. Okay, so now here. So in the chromaticity diagram, where are the different LEDs positioned? Okay, so I'll tell you something. Okay, so around this point, you have the InGaN blue LED, the classic blue LED of InGaN, which emits at around 450 nanometer, will be at this point in the chromaticity diagram. Okay, at this point, for example, will correspond to InGaN like blue green LED that emits at around 498 nanometer or 500 nanometer, this point. Okay, this point of over here will be again 505 nanometer blue green LED of InGaN. Okay, this over here at this point will be a green LED of InGaN that will emit at around 525 nanometer. Okay, 525 nanometer. This point is 520 nanometer, for example. This is 540 nanometer, the wavelength, okay, of the light. This is around 560 nanometer. Okay, this is 580 nanometer, that is corresponding to L in gap LED, L in gap, aluminum indium gallium phosphide LED that emits at 580 nanometer is there. This will be here 600 nanometer emission of LED. When I say 600, this is the peak wavelength. LED is not strictly monochromatic. This you have 620, 650, and this will be like 700 nanometer. Okay, so this will be, for example, 600 nanometer will be, for example, again L in gap LED, which is orange, L in gap LED, which is orange LED. Then you might have 615 nanometer LED, which is a red orange LED, again of L in gap. And then this could be around, say, 626 nanometer, which could be red LED based on aluminum indium gallium phosphide. Okay, aluminum indium gallium phosphide, L in gap LED on the red. So this is how different LEDs will correspond to the different points in the chromaticity diagram. This is the diagram which you basically, this diagram is used, it is drawn by X and Y lambda, which are used to mimic the human eye sensitivity. Okay, so you see that red and orange LEDs are pretty much on the periphery, but green LEDs are not so much on the periphery, but green LEDs are more towards the center. Okay, that is an important food for thought. And this is about this thing, but now how do you get white LEDs from this actually? So white, how do you get white light from all this? How can you make a white LED? You can have white LED of three categories. One is called dichromatic, which means you are going to use two sources to make your eye will sense it like a white. You can use blue and yellow LED. So if you use a blue and yellow LED and mix it in an appropriate quantity with some encapsulation, you are going to see like a white. So you will have two, one blue, one yellow, and the human eye will perceive it as a white kind of thing. This is called dichromatic. Of course, it will be the cheapest one, but also not the highest quality one. Then you have trichromatic, where you will mix three. You will mix blue, you will mix green, and you will mix red. So you will have blue, green, red, and then I will perceive it as white. It's a little higher quality. What do I say mean by quality? There is something called color rendering index. Okay, I'll come to that. Then there is also tetrachromatic. Tetrachromatic will include four colors: blue, green, cyan. Cyan is like blue green, around 500 nanometer is cyan green. Okay, cyan and red. So you will have four. 1, 2, 3, 4. This will have 4, and then you can make a white LED. The quality will of course be high in tetra, but also the cost will be high there. So essentially these three LEDs, they have a trade-off. They have a trade-off between something called color rendering. Okay, that means how good quality a color you can give. I will come to that. Something called color rendering index. Okay, they will have to trade off between color rendering index and efficacy of radiation. Okay, how efficient they are essentially in terms of saving power and giving light. Okay, if you want a higher color rendering index, you go for tetra chromatic LED, you will get very high quality light, but your efficiency will be low in the sense that you will have to burn more electricity to get that same color. Okay. So, there is called color rendering index. A high color rendering index light source means that you can see the color of the objects much clearly in high quality. This is important in shops, in some offices and homes and all, in grocery stores, when you for example have fruits and vegetables, or you have expensive jewelry or clothes in the store, branded clothes and all these very nice fruits and vegetables. If the color, the white light color that is shining on top of the clothes or vegetables has a low color rendering index, then those things will appear very soggy, very bad. People will not buy. So you need very high color rendering index bulb. Okay, very high color rendering index bulb, which are used in shops to display things, because they give a very brightness and very colorful appearance. Okay. Typically a good, it should be in a scale of 100. So if you have a color rendering index of 100, it means that the best quality. Okay. 90 or above is very good, but 70 or low is pretty bad. Even 80 is not so good. Okay. If you have a lower, so this will give you higher color rendering index, this will give you low color rendering index, but this will give you higher efficiency, this will give you lower efficacy of radiation. Okay. So that is important. See, quality of light will not matter as long as it is bright in terms of places like parking garage or street lights, parking places, staircases. There you just need to light up. You don't have to display something very gorgeous. Then you have to use a low color rendering index, because you get higher efficacy of radiation, right? Higher efficacy of radiation. So, the material that is used to when you just cannot mix some material and expect to always give you white light. For example, the classic white light made of gallium nitride or indium gallium nitride, you have a blue LED, and that is actually converted to white light, but there you don't have a yellow LED separately, but that will increase the cost. What you do is that you have the blue LED and you have a coating of phosphor around it, so that it will, phosphor will absorb and emit in yellow, and that yellow and blue will mix to give you light. So what is phosphor? Phosphor is not actually phosphorus, by the way. Phosphorus actually is a complex, it's called YAG. YAG is a very yttrium aluminum garnet. It's a very complex, like a oxide you can say, and you dope it or you mix it with something very rare earth like cesium for example, or yttrium or iridium or something, some very complex, or noble earth material. Then this complex is called a yttrium aluminum garnet, YAG kind of thing, and this is called a phosphor. If you have a blue LED covered with phosphor, then it will convert to yellow, and that yellow and blue will mix to give you white. Okay. So essentially what happens is that if you have, this is the optical power intensity for example, and this is your wavelength, then the blue LED actually is emitting like this. Okay, it's emitting at around 450 nanometer, but there is also there is also a yellow that will come like this. Okay, that yellow will come around 570 nanometer for example, or 600 nanometer. Okay, that comes because of phosphorescence. This phosphorescence comes around because the phosphor coating converts that by Stokes shift, and these two will mix up and give you white LED light, and that white light is actually that comes out in your white LED. Okay, essentially what happens is that a fraction of this blue light is absorbed by the phosphor and is re-emitted in a longer wavelength yellow, and both of them will actually give you the white light feeling. So the way you give this phosphor is that, suppose you have this LED encapsulation and this is your blue LED. Suppose this is your blue LED, this is your blue LED chip. Okay, this is your blue LED. Then you will have phosphor here. Okay, let me draw it here. You will have phosphor particles, this yttrium aluminum gallium things I told you, these will have phosphor particles here. Okay, and that is your encapsulation. So when the light comes out, blue light comes out, this phosphor will absorb and convert to yellow, some of them, and some of them will still come out as blue. So those blue and yellow mix up and give you the color of the white. The way you can distribute this phosphor also has a lot of things like proximal distribution, conformal distribution, and so on. Let's not go into that so much, but that is how white light LEDs actually emit, are emitted from your blue light. I keep telling you that if you stare into a white LED, you will see actually it's blue. So, so that is what about white LED and the color sensitivity functions and so on and so forth. Okay. One last question that I'll leave it with you, and then you think about it. Maybe I'll not tell you the answer. Is that human eye is roughly sensitive to 380 nanometer to around 750 nanometer. That range of wavelength to which human eye is sensitive is typically around 400 nanometer, right? This is the range, the delta lambda, over which human eye can be sensitive. Not exactly 400, slightly less than 400, but it's okay. So which means human eye can differentiate color in this range. Now human eye definitely cannot distinguish color at 1 nanometer. For example, 520 nanometer is green. If you show me 520 nanometer and if you show me 521 nanometer monochromatic light, human eye cannot differentiate that, because this is too short a difference, right? But human eye can differentiate 50,000 shades of color. Human eye can differentiate 50,000 shades of color, but human eye can only be sensitive to around 400 nanometer of wavelength. But there are 50,000 colors that human eye can differentiate. Does it mean that human eye can differentiate every 400 by 50,000? What is that? That is like almost 0.01 nanometer. Does it mean that human eye can differentiate every 0.01 nanometer wavelength? No, it cannot. So how is that there are 50,000 shades of color that we can differentiate? How is it accommodated in only 400 nanometer of wavelength? Do you know? How can? So that is a question that I leave it with you. Please feel free to talk to me and email me or discuss with me about the answer. But this is an important question you should think about. So we shall wrap the class today here, and we are done with LEDs. So we have finished all the discussions that we needed to do for LED. Today's lecture was mostly on human eye sensitivity function, colorimetry, chromaticity diagram, and how white light is emitted, what is color rendering index, and how we perceive the light of different quality, how white light LEDs are made with blue light LED using phosphor coatings and so on. And those are the things, and these are the quantities that are only specifically mentioned or discovered or used for human eye sensitivity. Okay, we do not use those terminologies for all the other wavelengths like UV and IR. But anyways, so optoelectronic portion of this syllabus is done. We are now familiar with solar cell, photodetector and LED. So the remaining few lectures that are there in this course, we will go with the different types of transistors that are required for different kinds of applications, and also if time permits we can go through some of the steps of practical fabrication to get these devices, this fabrication and clean room processes that enable these devices, whether it is optoelectronic device or electrical device. Okay. So thank you for your time. We will meet in the next class with starting with application of transistors in different areas. Okay. Thank you.